Oh, sorry. Is that recording is now on? Yeah. Okay. So injectivity was discussed, and it's very important. Then there were some examples. Not going to go through those examples again. There are several examples in the book material that you can study. One thing we mentioned in this example, one of these failed. We had an injective and not injective and surjective, and not injective and not surjective. But then the one that was injective and not surjective, that failed. And the reason is that when you talk about finite sets, then you're mapping element to element. And if you have an injective function, then for each element in your domain, you have a unique element in your codomain. And if they are the same size, the domain and the codomain are the same size, then every element of the codomain gets hit. If you think about, A goes to some of these, B goes to one of these, C goes to one of these, and D goes to one of these. So there are no more empty spaces left or empty slots left. So this is known as the pigeonhole principle. Not going to go in depth into that, but in discrete mathematics and in the very groundwork and the very foundations of mathematics is often based, you can base the concept of counting on the concept of injections. So we don't know how many elements there are in the set. We don't know how to count, but let's say that we know what an injection is. Then we can say that at least these two sets have the same number of elements if every injection is also a surjection. And then that's a concept of counting that we can introduce. And this is not the topic material for this course, but I like to explain that when you talk about, when we talk about stuff that is touched upon in discrete mathematics, then you should be aware that that's one thing that you may want to study in the future if you study mathematics a little bit more. These seem simple enough properties, and they are simple, intuitive stuff, but the mathematics of simple stuff is actually surprisingly hard because it's so abstract. We're not luckily going to talk about too simple stuff. The stuff that we're going to be talking about, differential and integral calculus, is actually pretty complicated, which makes it, weirdly enough, a bit easier maybe. Okay. So there we had the composition function or the composite function. We talked about that. We had some examples. I'm not going to go there. We needed to talk about increasing and strictly increasing, and then conversely decreasing and strictly decreasing. We can actually prove that if it's a strictly increasing or strictly decreasing function on a certain interval, and if that interval is the domain, then it is in fact injection, if it's strictly increasing. Because if you have two elements that are different, x and y are different, then f of x and f of y must also be different. Because if f of x and f of y are the same and x and y is different, if it's a strictly increasing function, then that results in a contradiction, because you cannot have this equal and then these not equal, right? Because one of them is bigger if they're not equal. We'll encounter that maybe a little bit more later, but again, this is foundational stuff that we don't focus too much on in this course. We can add, multiply, and so forth functions, and these was just something that we needed to discuss. But now to the new topic, elementary functions. So what does it mean that something is an elementary function? So elementary functions are those functions that are built from certain operations that we can easily define, let's say. Because you see, if you think about a function and its graph, and I said that the function is fully characterized by its graph previously, and you are it's fully okay for you to think of the graph as the curve that describes the function, right? You draw the curve and that's the graph, right? There are literally infinitely many ways of drawing that graph. I mean, even more than infinitely many. I mean, so vastly many ways that we can't even properly discuss that how many different functions there are. Only a few of them really are what we call elementary functions. Elementary functions are those that are easily described, and mostly what we focus on in this course are elementary functions. However, I must tell you, because we're dealing with differential and integral calculus, these calculus operations can result in functions that cannot be described using these elementary functions. There will be examples. What does that mean in practice? In practice, from the point of view of this course, it means that, for instance, if you are asked to find the integral of some function, then that integral may be such that there is no way to describe it using elementary functions. It is possible. The derivative of an elementary function is always an elementary function. So that can be done. That can be done fairly easily. But it's not so with the integration operation, right? And here are some of the examples of elementary functions. So, for instance, the constant functions, fairly easily. Let's say we have some real number a. So if we have a function that maps always just f of x is always a, that's a constant function. This is fairly easy function and fairly easily described. I'm just thinking, is there any there's someone has dropped in. Did we start? Someone asked, did we start at 14 sharp? Not really. We started at 14 sharp discussing stuff, but I only just now started this actual proper material. And don't worry. In the future, I'll see how the poll goes, but well, it's actually not as clear cut winner this 2 o'clock sharp. So yeah, it seems like it's more popular 2 o'clock sharp, but then yeah, we'll see how it goes towards the end. Don't worry, this is still recap material, so and this is going on video, and none of the group work will start before quarter past, so no one will miss anything really important if they don't. Oh, I accidentally did this. So constant functions are elementary functions, the most simple elementary functions. Then power functions, like if a is a real number, then power function is of the form f of x is x to the power of a. And because a is any real number, then this includes roots, like the square root is a power function because it's the x to the power of 1/2. The cubic root is a power function because it's x to the power of 1/3, and so forth. So this should be familiar to all of you. Exponential functions, if we have a non-negative real number a, then power functions, it shouldn't be power function, it should be exponential function. There's a typo there. So the slide says power function, but it's exponential function, not power function. Exponential function is something that is of the form f of x equals a to the power of x. Just a quick check that you are following what we are talking about. Think about this very quickly. Why do we require a to be non-negative? Anyone? If we do an exponential function, why do we require the base of the exponential function to be non-negative? Well, usually we require it to be non-negative because then these exponential functions are defined so that x can be any real number. If a is negative, if a is negative, then x is very much restricted because then we have roots and the complex fractional exponents and so forth. They would result in complex numbers if we have a fractional exponent. So we cannot have that. So we for the exponential functions, we assume that the base is non-negative. Then we have logarithmic functions. Their relationship to the exponential functions should be known. You guys understand what they are. And then there are trigonometric functions. We'll talk about a little bit about the definition of how trigonometric functions are defined. Some of these definitions or this intuition for the trigonometric functions, mostly we use the sinus and the cosinus, or the sine and the cosine. Tangent is very useful in some cases. We already saw in the exercises that you can use the tangent function to create something that works really nicely for the example of some interval mapping to the whole set of real numbers. And in addition to these, any and all functions that can be obtained by adding, subtracting, multiplying, dividing, or composing the functions that we listed here. So for instance, I deliberately did not mention the hyperbolic functions, the hyperbolic sinus and the hyperbolic cosinus, because those can be defined using the exponential function addition and division and constants, right? So I'm not here to give you a cornucopia of functions, how they behave, how they are defined, and so forth. We'll focus most of our attention when we talk about integration and differentiation. We focus most of all of our efforts in this particular class of functions, the elementary functions, and then talk a little bit about what happens when we add, subtract, multiply, divide, compose. So I mean, if we can find the derivative, for example, of each elementary function, and then we know how to do derivative of, let's say, a composite function. If two functions are composed, how do we find the derivative of that if we know? So there's f of g, for instance, f composed with g. If we know how to find the derivative of f, find the derivative of g, how do we find the derivative of that? We look into this, how this is derived, how we can do this. The integration will be a little bit different, or a little bit more problematic. It doesn't work quite as easily, but there are tricks and things that we can do there, and I will teach you some of those things so that you learn. Okay, there are some concepts regarding symmetries. We can talk about different kind of symmetries of functions, but the easiest ones are symmetries around the origin or symmetries around zero. So what we call an even function is a function such that f of x is equal to f of minus x. So, you know, a function gets a value, the same value regardless of x being negative or not. And then an odd function is a function that has this property that if you take the f of minus x, then it reverses the sign of f of x. Just give me just a second here. I'll have to pause for a little while. You may be familiar with this phenomenon. Okay, so here is a review. Let's do our first division into groups. I'll divide you into 6 groups, and within each group, um, you should discuss this idea, demonstrating that if n is a positive integer, then the function defined as x to the power of n. So the power function x to the n is odd if this n is odd, and even if this n is even. So discuss this in the group, and see if you can find a way to, what, you don't have to prove this, but check it out, and you know, how do you prove this? How do you prove this? You know, not, you don't have to prove it, just discuss it. And before you start discussing this, this thing, there will be 4 people in each of the groups. So let's say that what you will do, I hope you will see the list of people in your group. Then the first person whose name is mentioned as the first person on that group will have act as like a chairman, in the sense that you will go through a quick round of introductions first. You say your name, where you are from, and then you know, move to the next one. And once you've done that, you can also mention something nice about today. I know this sounds ridiculous, but do that. Mention something nice that you have encountered today, the nicest thing you've seen today, very quickly, or heard, or whatever. And then proceed with a short discussion about, in the group, about what do you think, how you would prove this, very quickly, just a few minutes. Then after I close the rooms, the person who acts as a chairman then will drop in the chat box a quick explanation, a very short explanation of how you would do this, like what kind of strategy you do to prove the oddness or evenness. Okay, I'm going to open the rooms now, and you have, let me just check the clock. You have 10 minutes in the group to do this. So quick introduction, something nice about the day, then a quick discussion on how to prove this, and then when I close the rooms, the person whose name is first in the list, that's the chairman. The chairman will drop your answer on the chat. Go. Okay, and we are back. So, quick message from everyone then who were assigned the chairman of your group. A quick explanation on how do you prove or demonstrate that if it's a positive integer n. Okay. Right. That's from group 4. Others? Is someone speaking? Oh, sorry, my mic was off. I hope it hasn't been off for too long.
No, it was not off.
It wasn't.
No.
I had this, okay, good. Put the value into the function, once it checks out, that's good, yeah. Yes, this is what I was looking for. Yes, good, good, good. So the thing about it is that if you take minus x to the power of n, then that is actually minus 1 to the power of n times x to the n, right? So it means that, it equals x to the n if n is even, and minus x to the n if n is odd. Yeah, you can do it for the first couple of ones. You realize quickly that if you multiply x to the n with minus x, then it always just changes. I mean, you multiply with minus x one more time, so the exponent goes up by 1. It always, reverses the sign from whatever it was before. That's the point. All right. Okay, I hope you had some nice things to share with each other. Let's move on. So here were other review questions. We're going to skip these now. I'm going to just very quickly walk through those so that we can get ahead today. So explain how to use elementary functions to define the absolute value function for non-zero values of x. Well, elementary functions to define the absolute value function of x. Do you get any ideas how to do that? The absolute value it's actually a quite tricky function. It's not mentioned in the list of elementary functions. Yeah, exactly. That's good. That's good. The square root of x to the square, yeah, x to the 2. That's an absolute value. Exactly. Everyone got that. I think that was a good point. I said non-zero, but it doesn't have to be non-zero. I mean, it can be 0 as well. Yeah, that works. Good. I don't actually know why it says non-zero here. It's non-zero. It's just confusing because the square root works for 0 as well. Again, we can have odd functions that are increasing and odd functions that are decreasing. An odd function meaning f of minus x is minus fx. So this is very easy to give the example because we just saw that x to the n is odd. If n is odd, then the easiest one for an increasing function is f of x equals x, right? That's definitely increasing function. I mean, if x is smaller than y, then f of x is x, which is smaller than f of y, which is y. And then, to make it decreasing, well, just take the negative of that, right? Now, this is also odd because if you just put in minus x in there, then it just becomes x, and it changes the sign. I didn't have a third question here, but these are simple review questions. You understand how this works. All right. One way to define, and this is something that is harder to do. You can't always do things with elementary functions directly. So what we do is we define them in a piecewise manner. And that means is we usually just chop the real numbers or whatever the intended domain is into pieces. And if there's only a couple of pieces, which is usually the case, we do it so that we just say f of x equals, and then we have three possible cases. If x is positive, it's 1. If it's 0, it's 0. If it's negative, then it's -1. So, you know. And then here would be another review question would be, define the absolute value as a piecewise function. And if you define it like this, I leave this for the next review task, which we will have while after we've done a little bit of this material, but we will encounter this, and just as a like a taste of what's to come, you know, it's very often the thing about piecewisely defined functions is that this happens when we have non-continuous functions, like functions that have a quick jump, like in this case. This changes from -1 to 0, you know, just jumps at 0 and then jumps right to 1 when it's positive. So this is not continuous, which we haven't defined what continuous means, but we'll get to that in the next lecture. And piecewise, there's no way to define this directly using these elementary functions. Piecewise functions usually happen when there is when you have a problem where we have something happens at certain threshold and a switch is thrown or something like this. We'll see some examples. These are actually not very easy to handle when it comes to differential and integral calculus, because then, you know, the discontinuities, well, as long as it's the number of pieces is small, then what we can do is we can just, usually what we do here is that each of these is an elementary function. In this case, there are 3 constant functions here. So whatever analysis we impose on the function, we do it for each of the regions, each of the pieces separately. And then we get some kind of result. Like if we find the derivative or find the integrate it over some region, then we cut the region to these pieces and so forth. So this is what we do with piecewise defined functions, right? Well, here's the important part. I didn't draw a picture here because I'm really bad at drawing pictures. The trigonometric functions. So very common way of defining the trigonometric functions is using the unit circle. And let's see if I can find the picture. I think I'll just steal that picture from the book, and then we can discuss these trigonometric functions using this. Just go into this and I'll share, not that, I'll share this one. Okay, so now it has switched to this view from the book, right? Everyone can see this, right? Can everyone see this? Yeah,
yes.
Good,
Yes.
good. So we usually use the unit circle to define this trigonometric functions. They can be defined using they're called trigonometric functions because there are functions that pertaining to the triangle. So a triangle is it can be thought of as one of those functions, you know, a triangle, and then, you know, we have the trigonometric functions which have a measure of some that deal with the angle, and then usually some proportion of different sides of the triangle. That same analysis can be brought to bear on when we define it using this unit circle. So usually is we think of the unit circle, and if we look at it closely, then if as we start increasing this angle here, we can thought this mentioned S here, that's the length of this circle or this arc here. And then when we're dealing with unit circle, then this angle is measured in radians, and the radian measurement unit means in fact the length of this arc at that angle. So it's actually how far along this arc we've traveled, or along this circumference we've traveled. And then the full circle is 2 times pi, and that's the whole circumference of the unit circle, the unit circle having the radius of 1. And we don't talk about degrees. It says in the book it's usually degrees, but I don't like to talk about degrees at all. So whenever we're talking about angle, it's always in radians, never degrees. If you feel you want to talk about degrees like 360 degrees, 180 degrees, and so forth, then please learn to transform those into radians. It's fairly easy because usually we talk about angles like 30 degrees or 60 degrees or 90 degrees, which are easily calculated fractions of pi, right? Because 180 degrees conforms to pi, which is 1/2 of the circumference, and then 90 degrees to pi over 2, and so forth. So we can these are fractions of pi, these usual angles. And whenever we're dealing with, for instance, triangles, then the maximum degree is 180, which is pi, and they always sum up to pi, these angles. So there's always in a triangle, the corners are the corners of the triangle, or the angles of the triangle are always some fraction of pi. And here, all this hubbub about that, but here's a nicer picture. If we have a point on the circumference P, which is denoted by X and Y, it's got X coordinate and Y coordinate. And we've traveled some way, this is theta, angle theta, which happens to be also the length of the circle from here to the point P. Sorry, there was something, no worries. So length of this circle. And we define the trigonometric functions in such a way that the sinus of this angle is in fact the y-axis here, and the cosinus is the x-axis at this point. And then the tangent is just a proportion of those. And those who are familiar with how they are defined in triangles. Well, in triangles, the proportion of the sinus in a right triangle. So when we have a right triangle, meaning that it's a triangle where one of the angles is 90 degrees, let's call this X, Y, and let's say D, well, let's call that Z. I'm going to draw a small picture here. So you are familiar with, let's see, here's a right, triangle where there's a right angle there, right? And if we have here, I'll change those into a little bit different. So let's call that Y and X, and then there's my theta, right? So if I have a triangle like this, then it's actually this exact picture. So you can think of this is the X, this is the Y. And in right triangles, the sinus is sometimes defined as so the sinus of this angle is the proportion, you know, this opposite side divided by this hypotenuse. So in this case, it's simply y, but because this is always 1, this hypotenuse in this triangle, then it's just y. It's y over 1, which is y. So if you've learned the characterization of these sinus and cosinus in the right triangles instead of this unit circle, then it's actually the same thing. It results in exactly the same thing, obviously. If you think about this in a circle with a larger radius r, then that corresponds to a right triangle where this hypotenuse is in fact the length of the radius of the circle, and then we have the cosinus and the sinus as the proportion of the one side and the hypotenuse, just like if you've learned this with the right angle triangles. So this is, it's the same thing. We're not going to use a lot of time on this, and not going to try and hammer these through. Not going to focus on you know, this regular courses. A lot of them focus on, you know, how do you, what is, you know, the sinus of 2x is equal to something. You can express it with cosinus and sinus and something like that. We're not going to do that. We're not going to be focusing on the heavy algebra. Like I said in the exercises to some of you, simplifying simple formulas, I would expect and wish that you learn to do those by hand, but then the more complicated memorized formulas that you may have learned in high school or whatever, that's not necessary here. So you are, if it gets hard, use some software for the heavy algebra, because I mean, my goal here is to teach you the way of thinking here. It's not about doing heavy calculations by hand. It's a bit different when we talk about differentiation and integration, when we try to learn how those the composition works, in the sense that we have you know, we have a function that is composed of different ways. It's, you know, there's multiplication, and then there's a composite function and division and whatever, and we need to find the derivative of the integral of some kind of this more complicated function. Then there I would not use software. If I were you, you are allowed to, but I would not use that, at least not in the ones that are the exercises where you're supposed to learn how to do this compositionally. So, you know, but for the simplification of formulas, especially memorizing of these different formulas for the trigonometric functions, that's unnecessary at this point. There is, however, one formula which I would want you guys to, you know, completely and utterly remember, not remember by heart, but just understand because of the way this is defined. And this is the fact that if we are talking about every point here on this circle, if we look at this circle, and like I said, this is the unit circle. So the unit circle points are those points which are exactly at distance 1 from the origin. And that means that every point on that circle satisfies the equation x squared plus y squared equals 1. Right? In fact, you know, x squared plus y, the square root of x squared plus y squared is equal to 1. And you can see it also from the fact that this is the triangle, you know, the right triangle formed here. So that comes from the Pythagorean theorem directly. And that means that whenever there's an x, y points, you can think of them as the sinus and cosinus of this. So x is the cosinus of this angle, and y is the sinus of this angle. And regardless of what this angle is, the cosinus squared plus the sinus squared is equal to 1. So that's where it comes from. So that's why the square of the sine and the square of the cosine is always 1, if you add them together. Okay, I'm not going to use the second and the cosecant and the cotangent because they're just the inverses of these. If you do a lot of analytic geometry and a lot of trigonometry and things like this, then you need sometimes use these. You need to sometimes use these functions, but I'm not going to use it here. We may do some, if we have to talk a little bit about complex numbers at some point, even though the functions we deal with are real functions, that we have to talk a little bit about complex numbers in certain points. Then we can use this cosinus and sinus as a way of transforming the complex numbers into polar coordinates, and the polar coordinates can be thought of as having the angle here, and then there's x and y. Then we can use the sinus and cosinus to do the polar coordinates thing, but we'll return to that later. So, but this is something that pops up everywhere in mathematics, and it will pop up in this course as well. All right. Let's see what time it is. Okay. Yeah, we still have time. Let's see. I'm going to switch to this slides now. Here's the same thing, really, what we talked about there, but I think the book had a nicer picture, so we moved there. Apply this to geometry. We already talked about the inverses of functions. So we have this definition is f of x is y if and only if the inverse of f at y is x. And this needs to be injective because otherwise this equation's right-hand side would have many solutions. Like if you have, you have a function whose value is y, then its inverse at x, then its inverse value should be x. But if the function has the value y at multiple points, then its inverse is not defined clearly. I mean, functions supposed to have a unique value, and then it doesn't have a real function as an inverse. It has to be surjective because, but we can always do it. If we have some function f that maps a to the whole real numbers, well, we can always just find the image of a and then restrict our codomain into the range. And then if it's injective, then we get an inverse. So here's some discussion. For simple elementary functions, discuss what their inverses are, if such exist. How do you have to restrict the domain to make sure they have inverses? So now this is another group task. Let's go back to this set of elementary functions. Some of these, of course, do not have inverses. Some of them have inverses. And what is the domains of the inverse? So let's do the same group thing now. Now you know each other. You can talk. So there's no need to do the introduction. It's the same groups as before. So bit by bit, go through these. Which of these functions have, and in what cases do they have inverse functions? The constant functions, power functions, exponential functions. And if they don't have inverses, then is there a region which you could restrict to, so that if you restrict the domain, can you make them have inverses? And what the inverses are. Constants, power functions, exponential, logarithmic, trigonometric functions. So I'll give you 10 minutes per group. Every group has, all the groups, I'll divide you again to these groups, the rooms. Discuss these. You have 10 minutes and explain how to find the inverses of these classes of functions. What are those? And do you have to impose some restrictions on the domain? Can you have the whole real numbers, or do you need to restrict it. And of course, the same with the codomain. I mean, do you have to restrict it? All right. I'll give you 10 minutes starting now. Okay. Yes. So there's also one. So first of all, what about constants? Can you find an inverse for those? And like there was a one question answer on already. There are no inverses for constant functions. I'm not fully, I don't, yeah, the a, yeah, if you have a to the x, if f of x is a to the x, then I'm guessing this art means that it's the eighth root, the root a of, yeah. And for base a exponential function, the inverse is the base a logarithmic function. Okay, that's good. So your group has found these. Those are all, you can say that those are correct. So now the question comes, how do you have to restrict the domains for those to be injective or to be defined in general even? Did you find a way to do that? How do you restrict? Well, let me just give an example. Let's say we have a function x to the power of a. That is true. If a is, yeah, if a is 0, this has no inverse, obviously. Well, what if a is negative? Well, I'm not sure. I'm just having to double check. Well, it's non-negative real number. I'm sorry, power function, some real number. Yeah, if it's some real number, a power function. If a is negative, in this case, then what restrictions do we have to make for this power function? You know, the domain. Well, what happens if a is equal to, oh, sorry. What happens if a is equal to -1? Can we take all the real numbers and we can be happy? Well, obviously not, because if a is -1, then x to the power of a is in fact 1 over x. And it cannot be 0, right? So if we have a negative a, then 0 is definitely out of the question. Also, if this is not an integer, if a is not an integer, then we have problems with negative numbers. For instance, if we have x to the power of 1/2, that's actually the same as the square root of x. So we have to restrict the domain to x being only a non-negative number. That's what I was aiming for. How do you have to restrict the domain to make sure they have inverses? I mean, obviously you need to have non-negative real numbers and so forth. Well, for the exponential function, there seems to be no restriction at all. That's not a problem. What is the proper codomain for the exponential function so that it has an inverse? So if you have something like a to the power of x, this is definitely well defined. Let's say a is some positive number. Doesn't matter what positive number it is. It's well defined regardless of what x is. We can probably all agree on that. And its inverse, already mentioned, was the logarithm, base a logarithm of y. But Now the question is, what is the codomain? What values does a to the x get if a is a positive number? Anyone? Well, if it's a positive number, then a to the x is definitely positive, regardless of whether a is, whether x is positive or negative. If a is over 1, if it's more than 1, then with very small x, meaning very large negative x, we get towards the negative values of x, like minus 1 million and so forth, then it gets really close to 0. But it's never negative, is it? A to the x is always positive. And then the proper codomain in this case would be the set of positive real numbers, right? And by positive, I mean those that are actually strictly larger than 0, because a to the x is never 0. And because of this, when we talk about logarithmic functions, you cannot take the logarithm of 0, right? That's not defined. Okay. And then the logarithm, which is the inverse of the exponential function, that's defined for arguments or for variables, values that are positive, right? 0 not included. And its codomain is then the whole set of real numbers, right? You can get any number, any real number as a result. All right, let's move on. We already discussed the exponential and logarithmic functions. We define the exponential function as f of x is equal to a to the power of x, and then logarithmic functions can be defined as their inverses. One very important special case that will become more and more important in the latter part of this course is the base E, or the natural based exponential function. Depending on where you are from, it's either the Napier's constant or the Euler's number. In fact, the number itself was discovered by Jacob Bernoulli. So it's got a long history and several definitions with which we can operate. One of the classical ones is the limit, which we don't know how to define yet, but we can learn how to define limits, is the limit of 1 plus 1 over n to the power of n as n approaches infinity. So the history of this formula of how this E was defined, the history of this formula was that people were studying compound interests. And you have a certain fraction of interest that would be 1 plus r, which is yearly interest. But let's say that you accumulate it monthly, that would be 1 plus r over 12, and then you accumulate it monthly, so that's 1 plus r over 12 to the power of 12, right? So if you do it yearly, you have the whole principal, which is 1, and then you add the interest, right? This is how much you earn in a year if you pay the rent once per year, or the rate, the interest is paid once per year. But if you pay it semi-annually, for instance, then at every half year you pay r over 2, this much. You pay this much, but you pay it twice a year. But because at half of the year you pay half the yearly rate, and then you have the remaining year. But in that case, you're going to be multiplying these, because now you have this much money, you reinvest it, and you gain this much again. So So this is how much you get, this is how much you have at the end of the year if you pay it biannually. So if you pay it n times per year, then this will be your principal at the end of the year, how much you've gotten back. But then, you know, as n approaches infinity, what if you were being paid, you know, the interest constantly and you're reinvesting it? Then it's the limit as n approaches infinity, and it turns out that this will be e to the power of r. That's the limit. And in the case of r equal 1, then the limit of 1 plus 1 over n to the power of n as n approaches infinity, that's e. So we're not going to prove that this limit is, I mean, we don't have to prove that the limit is e, because we can just say that whatever e is, it's some number, but the number is this, that's the limit. And it has some really nice properties. What I can't really resist the temptation of mentioning these properties now. One of the great properties about this is that if we take the e to the x, you probably have heard of this already when you talk about derivatives. If you take this function, e to the power of x, then you find that its derivative, which you will learn shortly to calculate, the derivative of that is supposed to give you the rate of how fast it's increasing. And it turns out that the rate of increase for this function is exactly the value of that function. So the derivative of e to the power of x is in fact equal to the e to the power of x. And this is a very profound thing that affects a lot of mathematics that we will discuss during the latter part of this course. So that's why I wanted it to be mentioned here. So, and the thing is, of course, you'll learn in some examples that you can transform all and any exponential functions to exponential functions of the form e to the something times x using logarithms. Okay. Here are some properties of exponential functions and expressions. If you have a to the power of x times b to the power of x, it's just a b to the power of x. You should be familiar with this. A to the power of x times a to the power of y is a to the power of x plus y. And then the division becomes a negative, you know, a to the x divided by a to the y is a to the x minus y. And then the division, just take the x out and so forth. Well, the final task that I would impose upon you before we're not going to end, I'm going to give a couple of discussion, a little bit of discussion about limits. The task to take into account that the logarithm, base 2 logarithm of x equals y, if and only if a to the power of y is in fact equal to x. So using this, figure out how to derive these. What is base a logarithm of x times y? You already probably know these, but try and figure out, you know, okay, this is, I'm using a and y here. Forget about that. Maybe I should use in the headline, I should use the base, let's say base a logarithm of x is equal to z if and only if a to the power of z is x. So that's the identity. So base a logarithm of xy is equal to some number if and only if that number behaves in a certain way. And then using similar reasoning that we know from here, what do you know about the logarithm? You know already how these go. I'm assuming that you know how these go, but try to see if you can derive them. And this will be the last group session for you guys. So I'll put you into these groups and you'll have a few minutes. I'll give you I'll tell you shortly. I don't have my clock. I have to put my phone away. So a few minutes and then I'll give you a warning before it ends and derive these laws and try to do it in the group in such a way that you probably know how to do the logarithm of the product. You probably know, but try to see if you can derive it, sorry, using these rules, right? Try to do that. And You have a few minutes now, and I'll be shortly with you. Okay, so people are slowly coming back. I hope that this was only a couple of minutes, so I'm hoping that you were able to discuss. We are running a little bit out of time, so I didn't want to put too much time on that. All right, now everyone is back, I hope. All right. Now, firstly, now I hope one of each group will tell me what are these logarithms? How do you calculate these? And a quick understanding of how and why can you derive? I mean, I'm sure that many of you remember what the rule is here, right? So if you take the log, sorry, wrong. If you take the log of xy, we know that that's actually the log of x plus the log of y. But I think the way we can, I hope that you were able to come up with some kind of answer and you understood and had time to think about it. The way you can do this, that if log of xy is equal to z, then we have that a to the power of z is equal to x, y. Right? So we have a to the power of, let's call that u times a to the power of v. Sorry, let's mark that a to the power of u is x, a to the power of v is y. Then a to the power of z, x, y is equal to a to the power of u times a to the power of v, which is then, using the previous rules, it's a to the power of u plus v, right? Because we can take these rules here. The second rule. And then, well, that one is in fact equal to a to the power of z. And then we conclude that z is u plus v. But because a to the power of u is x, then that's actually u is, right? But then because a to the power of u is x, then u is in fact the log of x, and v is the log of y. Right. That's the kind of thinking I was hoping. Why I think this kind of thinking here is important is that very often the case is that we need this sort of thinking about, you know, going back and forth in some definitions later when we talk about the derivatives and the integrations and stuff. We have to figure out, okay, if this were that function and that would be its derivative, then what would that be, and so forth. Then we need this kind of going back and forth idea. The same for the, I'm not going to go through this other examples here. I mean, I hope you were able to do that. We are just have 5 minutes more from what I promised. I promised we end at 3:40, and that's when we will end. We will end from now on. This lecture will start at 2 p.m. sharp, and we end at 3:40. So we have 1 hour and 40 minutes. That's 100 minutes. That accounts for, we don't have breaks per se, but we have a couple of these group sessions. So I try to give a little bit more air into that, so that you can use that to wind down. It's not so big a deal. I'll give a small task, and you can use that to have a small break, have a small chat with your fellow students, and so forth. So that accounts to roughly 2 times 90 minutes, 2 times 45 minutes, which is roughly the recommended time. But before we stop, I'll give you a glimpse of next week's topics. We will be talking about limits and continuity and derivative. So it will be quite heavy on definitions, like before. The definition of a limit, I'll give us, there's a standard and non-standard definition. And I'm showing this to you now. What I want you guys to do for next week is to read the chapter 2, but not the first parts, just chapter 2. I'll give I think it's chapter 2.2 or something. 2.1 you can read if you feel like you want this kind of ideas to cover these kind of ideas that are there. But the topics that I start from is from chapter 2.2 in the book. And what I will start with is the definition of a limit. And I know that it's common to think of a definition of a limit as something like, you know, I'll draw you a picture like, let's say I have a function whose graph looks a bit like this. And let's say that the thing is that there on that, I draw this dot. There, exactly in that point, the function is not defined. Something weird happens. We know that there is some kind of a point there that we get very close to, but not quite necessarily to that point, but we do get to that point. The standard intuition is of limit is, no matter which direction we come from, as we approach this point, we approach this x-axis. I'll draw here. That's the x, and that's the y, and that's the x. So no matter where we come from, as we approach this x here, then the value of the function approaches this y, right? That's the common idea of limit. But this idea, that this definition is the standard mathematical definition in some sense, and you got to understand that this definition captures that intuition, although it's not necessarily clear how and why. And I wrote it even this in an even more abstract way. So it says that when we have any open interval that contains this y, open interval containing this y, there exists some open interval that contains, sorry, there's a mistake here, ix0, right? There is an open interval around this x0, it should be ix0, not y. ix0 that contains this x0, such that for every x, every element on that interval, this function value belongs to that interval. So in essence, there's a standard, the standard one is to mention this so that for every epsilon greater than 0, there exists some delta greater than 0, such that when we are closer than delta to this x0, so when we get this close, so this means simply that there is an open interval, right? Either larger or smaller than x0, but not by more than delta. If you are this close to this x0, then the function is at most this far away from y. And, you know, it means that when we squeeze this closer and closer to y, we can always find some small range there around this x0 such that everything remains in this small region. So it means, and I'll draw another picture which clarifies it. I think of this as I've zoomed in quite a bit into that picture. So it means that no matter how narrow this region we pick, we can squeeze in at that top, you know, squeeze this region, you know, this up-down region to as small as we want. We can always find a region here between these, such that if we just stick to that region, then the values will always be, you know, never vary more than this much around that point. It means that when we squeeze our view, we shrink, so closer and closer we shrink towards that y, then, you know, there's always some region so that when we move around that, then it doesn't go further than, no matter how small, it never goes further from y than this. And it means open interval. We don't have to take exactly that point, so that it's not sensitive. If we move just a little bit from this point x0, it cannot cause a sudden jump out of that window. That's the intuition bit of the limit. So it means that as we zoom in on that point, the function will not, somewhere when we get nearer and nearer, it doesn't go anywhere off the rails when we get close enough. Right. Now, this is what we will be talking next week. And I just wanted to give you this so that there's something to contemplate. I will draw you the agenda for next week today, so that I will write it on the Moodle page. Next week's exercises and the model exercises for this week will be available on Monday afternoon. And also I will update the lecture slides so that next week's lecture material will be covered. So it will be contained there on Moodle page by Monday afternoon. So you now have the weekend and until Tuesday to finish your weekly exercises. Yes, I will publish this recording in Moodle as well, definitely. Yeah. I'm going to try and learn for next week's lecture, I'm going to try and learn new techniques on how to better share material in the video, because the video recording of the Tuesday lecture was not quite up to the standard that I was hoping. I'm now going to stop recording, and I thank you all for attending here. I'm going to try and see next week if we can activate a discussion so that it's visible here on the recording as well a little bit more.